Okay, so my name is Sergey, and I am from the University of Pittsburgh in the US. I do three things lately. One is I try to organize things in support of science in Ukraine. I'm originally from Ukraine. Many years ago, I was born in Zaporizhia, and of course, Ukraine has been in the news for very sad reasons. For instance, these broken buildings are actually physics buildings in Kharkiv. This gentleman is standing in what used to be his lab in Kharkiv. So if you have not seen such pictures, I just wanted to show you. Kharkiv, for one, is a place with a very long legacy of scientific excellence. For instance, Landau, or no Landau, like Lev Landau. Okay, a couple people know Landau. What about Shubnikov? Shubnikov. Yes, very good. Yeah, so Shubnikov was actually executed by Stalin, but he worked in Kharkiv. Yeah, but Ukrainian science keeps going. Maybe it's not the highest profile, but for instance, I always highlight this paper by my now friend Valentin, because this material, like telluride, is a very interesting material. It's nearly topological, but it has a dielectric constant of 1000 at low temperature. It's crazy. And I work with these nanowires now, but he introduced me to this material 10, 12 years ago. He said, look at this, this should be interesting for you. It has strong spin-orbit interaction, many interesting, it has low effective mass, so a lot of the things that you need for instance, topological superconductivity like Majorana modes, you can find in this material, and so we are working on this together. Another thing I work on is investigating unreliable papers in our field, and I'm happy to talk to you about this, but I did not put any slides on that directly in this stack of slides that I'm going to show you, but I'm happy to talk about it. However, I will give my lectures in this spirit because, like Misha said, I'm an experimentalist, and I will talk mostly about my own experiments, kind of a journey. I was maybe fortunate from my PhD time. My second paper was already a negative result, like an alternative explanation to some of the things that somebody claimed was an interesting result, right? And so I was kind of brought up in this spirit that you have to look for alternatives because, what I'm kind of when it comes to science, I try to stay like zero cynical, right? I really love making discoveries. I was lucky enough to make a couple, not the one maybe you know me for, but some others that I will show you here. But I want them to be for real, like a real discovery, right? Not just write a paper to say, oh, look, maybe it's something, right? And then, okay, later, 10 more people tried the same thing and spent $12 million and okay, it didn't work out. Okay, but it could have been, right? No, I don't like this way of doing science. I want it to be for real. And so I will show you sort of some interesting data, but then I will show you that maybe it has a different explanation, right? So this will be like throughout the lectures a theme. So that's and of course my first and foremost activity is doing research in my lab. So here's a picture of my lab. I have 10 PhD students at the University of Pittsburgh. And we have this low temperature physics lab. These are cryostats, dilution refrigerators, 1, 2, 3, and there's another one around the corner. So we have a lot of them. So what you need dilution refrigerators for is to get to millikelvin temperatures where a lot of the quantum effects in mesoscopic structures come out because that's how energies work out. So the coherence time, as the coherence length increases. So larger and larger structures, you're going to see quantum interference and things like that. because the length exceeds the size of the structure. You can think from the point of view of temperature. So in quantum dots and semiconductors, energy scales are millivolt. And so that 1 millivolt is 10 Kelvin. So at 10 Kelvin, you will start seeing maybe something, but it will be very blurred and smooth by temperature. At 1 Kelvin, it will be better. Josephson junctions and things like that, energy scales could be 100 microkelvin, so that's 1 degree Kelvin characteristic energy. So you want to be below 1 Kelvin. And below 1 Kelvin, to get to below 1 Kelvin, you need helium-3. Anybody heard of helium-3? So there's helium-4 for balloons, right? And for getting to 4 Kelvin, there's helium-3 for getting below 1 Kelvin. And so eventually you need this dilution mixture of helium-3 and 4, so you need these machines. Another thing they have is large magnetic fields, because a lot of our experiments, what we do is Zeeman split some bands, for that you need like Tesla scale fields, so that's very conveniently integrated because it's already cold and you can have a superconducting magnet. So it's just if you have not seen such machines, it's not a big focus of my talk, but I just wanted to introduce it a little bit to you. And yeah, so this is what my talk is not going to be about, but it's maybe what you heard my name related to. And so I put all of this stuff in just one slide. I know there'll be other lectures related to this here, but more than 10 years ago, 2012, we wrote this paper where we thought we found signatures of this effect, Majorana zero modes in condensed matter systems. And so it comes from, well, you could say Ettore Majorana's work in 1937, where he was solving the relativistic Schrodinger's equation, called Dirac equation, and in that spectrum he found solutions that are what's called real, which means in terms of the operators that creation, if you act on a wave function with this operator, it's the same as acting with this operator. It's like creation and annihilation of a particle is the same thing. That was already unusual, but of course in condensed matter systems, it's a lot more interesting than what Majorana discovered because they're non-abelian. At least it's predicted that they're not abelian. There's no evidence of it, and there is also some doubt, theoretically, that it will ever be possible, but at least we're going based on this assumption that they might be non-abelian, and that means that these objects, well, they're not identical in a sense, or if you move them around each other, you acquire not just a non-trivial phase, not 0 pi or pi over 3 or 2 pi over 3, like in fractional quantum Hall effect, but you could also go into a different eigenstate, into a different degenerate eigenstate, and you could even define qubits 0 and 1 in this manifold of eigenstates. If you have more Majoranas, the manifold grows, and you can imagine an entire architecture of topological quantum computing, which quite a few people are, that's their declared goal, and at least one company that I'm not going to say out loud the name. But it's also interesting that, this idea, it's kind of, I mean, it's a cute idea, but it requires a lot of effort and a lot of things need to be degenerate, which in real life does not happen very often. Yeah?
Why Majorana is so interesting for the qubit? It's good for the store information, but it's not like a full qubit. We cannot do a universal control.
I agree with you. I mean, it's true, right? I mean, it's a complete, like, this is one of the examples of the way I don't like doing science this way, right? Like, there's this fairy tale, like, oh, topological qubit is going to be awesome. Then just look at this. Let me answer your question by just, like, carrying on, because I think it will be answered. So, for instance, look, this is a very nice paper, Litinsky von Oppen. It is actually a surface code architecture with Majorana zero modes, right? So let's take this picture and think about it for a second. First of all, why do we need a surface code? If you know what surface code is? Surface code is an error-correcting code for classical qubits, for conventional qubits. That is the most efficient code we know, and it's kind of a plane of qubits, and you have to do continuous measurements on plaquettes of qubits. It's a very I mean, I could, I guess, talk about that for half an hour, but let's just say it's a very difficult to implement code. You have to sort of continuously measure a grid of qubits, and when you stop measuring, that's sort of an operation on a qubit. But it requires lower threshold for qubit fidelity than just having one qubit and encoding one bit of information. And so the practical implication of surface code is that to encode one qubit, you need like 10,000 physical qubits, and that the people talk about the logical qubit, right? And now with topological qubit, it's supposed to be just like 2 or 3 Majorana modes, 2 or 4 actually, it cannot be 3. And that takes care of the 10,000, right? But now we have a surface code for protected qubit, right? So that already is a little bit interesting. Why do we need that, right? It should be protected. Right? And now, of course, in this particular implementation, every vertex of this colorful, so colors are the different type of measurements you have to do, like sigma x, sigma y, on the different plaquettes. So one plaquette like this 4 is 4 Majorana modes in the corners, right? You know, we have a difficult time establishing one Majorana mode right now, but now we need to put. But what's more, it's like a three-dimensional. Like you have one layer of Majoranas, then another one. So that's the kind of the architecture. And what I like the most is that it says step 1 here. So that's just like that's the starting point, right? Okay, but look, I don't think we'll ever build a quantum computer this way. But it's interesting to answer the physics question of whether this is possible, the braiding operation to move from one wave function to the other. And certainly just this one is what we've been busy since 2010 on this problem. And this is just sort of, can we establish the evidence that these quantum states are even present in these wires? And to do that, the starting point seems pretty easy. So you put a nanowire, as a semiconductor crystal, coated with a superconductor, like aluminum, very conventional. And semiconductor is also well-known materials, right? You know, CMOS and other things, lasers. And what you're supposed to see is a little feature in the middle of this kind of spectrum, which is a superconducting tunneling spectrum. These little ears are superconducting gap, and inside the gap, in a suppression, there should emerge in magnetic field this feature, and that's called zero bias peak. And yeah, we found it under the right conditions. Nominally, we read these papers by theorists and implemented this recipe, and we found what was predicted, right? And it's not what my lecture is going to be about, but I'm going to tell you that a few years later, for a couple of years, people thought we discovered Majorana. We got very famous. A couple of years passed, and it turned out there's another explanation for this. It's not Majorana, it's a bound state in a quantum dot. And that was fascinating, absolutely fascinating. But I spoke about this so many times. I'm just dreading to retell the story again, at least in full, to a high-level audience like yourselves. So I'm just gonna go in a different direction today. By the way, my friend here, Vincent Maurik, is also one of your lecturers, so you can also bother him about this. Now, still on this topic, I just want to highlight that the recipe to make this Majorana, right, that we had all these properties, non-abelian for qubits and for fundamental physics, particle, its own antiparticle. It's a relatively straightforward recipe. In 2010, I was already working with these kind of nanowires. So it's about 100 nanometer diameter rod of semiconductor. In this case, indium antimonide, indium arsenide was tried as well, germanium, other things. And it's already such a high quality object. It's a single crystal, right? So no crystalline defects in this whole nanowire. It could be microns long, so the crystal growth here is amazing. And then in this particular sample, we also coated with a very thin layer. You cannot see it, so it's marked by this line, and that's tin. It's superconducting metal, goes superconducting at low temperature. And so this is sort of where you probe measurement is a tiny probe. But look at the ingredients. Nanowire, superconductivity induced by proximity, proximity effect. Okay. I need you to respond to me because I really don't know the audience. Like you come from different countries and different backgrounds, so please engage with me. Yeah, play along because I have an infinite number of slides that I can tailor to different levels, so different backgrounds. So superconductivity induced by proximity. We will talk about what that means. Magnetic field and spin-orbit interaction is an interesting ingredient. It's a property of the band structure where in certain crystals that lack inversion symmetry or symmetry is broken by structure, like making an interface between a metal and a semiconductor. This term appears where the spin bands split like this, right? Zeeman effect, spin bands split like this. Spin-orbit effect, bands split like this, meaning depending on your spin, you have different momentum, so spin-orbit term, analogous to atomic spin-orbit, if you remember it from your kindergarten physics, how you joke. Anyways, I did not have it in kindergarten myself, it actually originates also in bands from the same atomic spin orbit, right? If you dig deep enough. But this is kind of the picture, and so this is just you just pick a crystal like that. Okay, diamantimonite has it, so check mark there. Magnet, I told you I have big magnets in my lab, and all I need is a nanowire with this shell of superconductor. Now, that's to make Majorana. Now, I told you we had a hard time making Majorana, proving Majorana. So we spent quite a bit of time and explored this alternative explanation, said, okay, there is another explanation for what we see, and then a couple years later, looks like that explanation explains everything. So it's not really another explanation, it's really the explanation. Yeah.
Is there some advantages of nanowires compared to the 2D gas or other platforms?
I mean, yeah, so in my other slides I have a whole cloud of ideas, right? There is maybe 20 different approaches to make Majorana. And, I think nobody has demonstrated convincingly, so no clear advantages to any of them. But when it comes to, if we could make it out of a 2D layer, and if you think about the qubit, the quantum computer picture I had, so then of course there could be advantages at that stage, right, in the future to scale it. Right. At this stage, whoever shows convincing Majorana will be the king for a while until. The question.
So when you speak about nanowires, we only speak about reverse spin-orbit, yes? And why we always doesn't have any system, 1D system that have Ising spin-orbit or something like this, no?
Oh, Ising like in van der Waals materials?
Yeah, like in van der Waals, split band not in this direction, but like this.
Right. I am not aware. Yeah, so that's a pretty special, even in materials like niobium diselenide, right?
Yeah.
It's there in one layer, and then in 2 or 3 layers, it's either decaying or not there anymore, right? So, but for instance, in a nanotube, which is a rolled sheet of graphene and a single wall nanotube, there is a very bizarre orbital related spin orbit due to the curving of the p orbitals like this, making a ring. And it's extremely strong, and I think that's maybe a little similar to Ising, but I don't think it breaks like that. It's still, but it's fairly useless unless you bend the tube. You have to bend it like this. Okay, now why do I show you these ingredients? Because finally I'm getting to the topic I want to cover, but okay, we have like 4 more hours together, so I think it'll be fun. Here with you, I would like to talk about my long-term passion from my PhD time, which is unusual, unconventional, exotic Josephson effects. Josephson effect requires 2 superconductors and a non-superconducting material in between. And so these are some examples of Josephson effects that I consider exotic, and I will explain why and bring you on board. You can argue with me that they're not exotic, or, but in this slide, what I'm showing you is that some of them require the same ingredients as Majoranas, right? Magnetic fields, in orbit, nanowire, right? And this one really is just Majorana, but exponentially harder because you need Majorana in one superconductor and in the other. So if it's a narrow window to find Majorana in one, then finding it in two, good luck with that. But that's really just another way to prove Majorana. And these are interesting because you can see just from the picture, right? This one is flipped compared to this one is offset, etc. But first we need to talk about what is the conventional Josephson effect. Anybody knows what the conventional Josephson effect is?
I mean, answering to your question, yes, it's under the coherent output of by this insulator.
Yeah, very good. And in the representation of phase difference versus current,
Sine.
a sine function, right? So we're going to talk about what this is, but what I like to call it is current phase relation, and so it's a relationship between superconducting current, zero voltage current, flows through the junction, and a phase difference across the junction, current phase relation. And the conventional one, known since 1960s, or even, 1960s, is a sine function. I equals sine phi. That's the conventional one. And so these, I think, if we accept that definition, these are all fairly unconventional, right? So this one is the most conventional. It's still a sine, but it's with a negative amplitude. So you wind the phase and current goes the other way. And that was the topic of my PhD. And I came to it a few more times in my career. This one is completely bizarre because actually this is from my PhD thesis. And I copied from these other guys, and even before them, Likarev wrote something, and they copied it from Likarev, I copied it from them. But these are sort of, physicists like these kind of theorem things, like to be like mathematicians. And so they say because this current phase relation is a manifestation of macroscopic quantum coherence in superconductors. And so it's really a property of a wave function. And therefore, the laws of wave functions have to apply to these relationships. And so for instance, if you wind the phase by 2 pi, it has to go to the same, right? Now, which one violates this?
The second.
Uh,
I mean, it looks like doesn't look really.
So this one goes down here, and just before pi, this one goes down, right? So this one actually is okay.
Okay.
This one's okay.
I'm already a bit lost. Could you repeat what the current phase relation tells
Okay, yeah, I'm sorry. How about this? I show this slide. How about this? Right, so Josephson junction is 2 superconductors, and you have to tunnel between them. Now, what is interesting about this effect is that, think about it as one wave function in the whole piece of superconductor on the left, and another wave function in the whole piece of superconductor on the right. The amplitude of the wave function is the superfluid density. So there's the number of electrons participating in superconductivity. And the phase is arbitrary. Right? And the entire wave function in the entire big piece of superconductor is just described by this one complex number. And that's it. And then the other piece is another number. But let's say it's the same material, so NS is the same. It doesn't matter. It could also be different. It still works. And now when we bring them close enough, but we don't touch them, we make a weak link between them. You can think of this wave function as evanescently decaying, right? Like decaying in a barrier, like a wave function decaying in a barrier. And so it goes from one amplitude down and from the other side, and so if there's overlap then the coherence is established across the superconductor. And however, naively what you think is, if it's in equilibrium, the phases will also equilibrate. Why? Because in quantum mechanics, gradient of phase is equivalent to current, right? Current is proportional to gradient of phase, right? Psi, gradient psi, minus psi dagger, whatever. I don't know. There's a formula. So which means if we try to pass a current through this thing, two interesting things. First of all, current can flow without voltage. That's supercurrent. And we study this signal, supercurrent. The second thing is when the current is flowing, there is a phase difference, right? Because gradient of phase is equivalent to current. So what we're going to talk about in this lecture is phase difference across the junction, phi 1 minus phi 2, and supercurrent as a function of that phase difference. And what Josephson, Brian Josephson, calculated in 1960s, which was a big surprise, by the way, is that this function is IC sine phi. If this is a simple tunnel barrier. And what is bizarre about it is that it means electrons tunnel in pairs, in Cooper pairs, that make superconductivity, right? That's very bizarre. Okay, so thank you for this question, and sorry for the slides out of order, but now go back to this, okay? So it's a wave function across the junction, and that means that it's 2 pi periodic, right? Otherwise, the wave functions will not, if we make a loop, for example, and it's not 2 pi periodic, there'll be problems making a single valued wave function around the loop. That will be a problem. So this has to be the case. But there is one here that violates this. This one, right? So because this one, it's a little subtle, but this is 2 pi. So this is the Majorana one violates it. And so when I wrote my thesis, this was not allowed. Even though I think Kitaev already wrote his paper by then, in 2001, but anyway, still, this was the sort of the dogma. Now, this one, second one, is the symmetry, right? If you flip the phase, you flip the direction of current. Yeah, it makes sense, right? So it's like voltage, right? Apply voltage this way, current flows this way. Apply voltage this way, current flows this way. So kind of the same way with gradient of phase related to current. Which one violates this? This one, right? It's not the same for plus and minus. In fact, even the amplitudes are different. This IC plus and IC minus are actually different. So when I was graduating in 2005 with my PhD, this was impossible. This was like, you know, a group of smart physicists would laugh you out of the room if you show them this. They'll be like, "Nah, this is not possible." Okay, so let's see. Maybe these other ones are okay. I don't know. Yes, they're not okay because it follows from 1 and 2, and both of these can be violated. Yeah, but you get the idea, right? So this one is also a little bit interesting because the period is not 2 pi, but it's pi, right? But this is actually allowed. I was already looking for it in my PhD time for this higher order Josephson effect, which means 4 electrons tunnel at the same time, not 2, but 4, higher order effect. Okay. So we're going to talk about these things. Questions? Good. Okay, so we covered this picture. So I really like this picture because, you know, the overlap of wave functions. But lately, like the last sort of 10 years, maybe when Majorana started, this picture of the same thing, right? It's the same effect, Josephson effect. But this picture became more popular, and they're both, you can calculate, get the same results both ways. But this one, you have to think like this. So the last one worked nicely when it's a tunnel barrier, so nothing, a vacuum in between. Here, let's put a non-superconducting metal or semiconductor denoted by N. So there is no Cooper pairs in this material. So there's no two electrons, there is only single electrons. And now there is an interesting process called Andreev reflection that can connect the two electron condensate of Cooper pairs here with one electron states here. And so Andreev reflection goes like this. Electron comes in, Cooper pair is created, and hole is reflected back. An electron hole is a particle above Fermi level, which is the occupied level, right? All of these states are occupied. And here hole is empty. No particle below Fermi level, right? So these are not particles and holes in semiconductors. Anybody focused on semiconductor physics here? Because, yeah, so those people get confused with like excitons between electrons and holes in the different bands. This is all metal, and this is just above Fermi level and below. So the energy scales here are, like I said, microvolts, and in a semiconductor it's volts, right? So that's the difference. So it's just confusing name. The name was the same. Now, in a junction, this happens again. A hole comes in, a Cooper pair is created. Now you have to, Cooper pair is two electrons, so it moves this way, or moves this way. There's a hole moves this way, Cooper pair moves this way, and creates another electron to make sure there's charge conservation, right? Two electrons come in and replace with electron hole going this way. Now, if this is a finite length, bizarrely, this forms a bound state. So this loop, electron hole loop, is like a bound state in a potential well. Potential well bound by the little energy scale called superconducting gap. And so you can calculate the energies of these states from reflection conditions. You get this arc cosine function, and you can calculate these energy branches for plus and minus delta cosine phi over 2. So that's the energies of these Andreev bound states. And it's a very simple calculation. So upon reflection, you get the phase shift, which is the phase difference between the two superconductors plus some constant, and you do continuity back and forth, and you get the spectrum.
In superconductor, we have a boson gas and the all occupied one state. Where from the holes and electrons that are below and above?
Yeah, so this is an interesting thing. So this picture really is friendly with boson gas, right? Because the entire boson gas is described by this wave function, which is a Cooper pair wave function. And then the two boson condensates overlap, and you get the Josephson effect, right? So it's very easy to see directly how that is. In this picture, it's kind of more of a fermion picture, because this electron hole, I guess it's you can think of this Andreev state as a many-body coherent state that is also couples the two condensates. Those are the words I have to say, but you just think of it as this mode mediating interaction between two boson condensates.
Mm-hmm.
Yeah. But what's interesting is these states have now been observed for a while. When I was doing my PhD, this was just a theoretical picture, which had no practical implication. But now we can resolve individual Andreev bound states, so they're definitely real. People make qubits with them. So this picture is kind of becoming, so some of the new students in this field anyways, they get trained in this view of the Josephson effect. They don't even fully understand or they're not used to thinking in terms of this. But when I was growing up, this was my sort of, it was harder for me to think about Andreev states. Okay, so remember this formula cosine phi over 2. So how do we get from phi over 2, how do we get to phi, right, for the conventional Josephson effect? Well, for that we need to plot these two branches. So this is the one branch, this is the other branch. And the next trick we have to do is, see these are two Andreev branches, the plus and the minus. Here where they're degenerate, the question is there a scattering between the two branches or is there not? And in most overwhelmingly situations, there is some kind of scattering. And what happens when there's scattering? They hybridize. the two branches hybridize. One is pushed up, one is pushed down. There is this anti-crossing. And you see what happens? Now it's a 2-pi periodic function. So when you change, this is a function of phase. Change the phase, you travel on the top branch, on the bottom branch, and it's 2-pi periodic. Now this gap is proportional to basically this constant tau, which is the scattering amplitude or transparency of the junction. And the picture really that connects my wave function overlap picture to this Andreev one is this one, which is a complete ad hoc thing, but we have to imagine there's a bound state here, right next to the superconductor. There's a bound state here, and there's an insulator in between, and there is overlap between the bound state wave functions, right? So this is how you go from this picture really to this picture in a practical way. Is that clear?
Yes.
Yeah.
What is the nature of the scatter?
There's always something, right? So here,
I just try to understand how to think about it actually.
Yeah, so-
I think I have this my bound pair which tunnels
yeah,
and they somehow like scatter to other
to the other bound pair, right? So really think about one bound pair here, one bound pair here, and in between a scattering center or a coupling center, and
yes, but what is basically like a scattering center? I mean like some impurity or
yeah. So in a real junction, it could be roughness, impurity. It could be some process like a phonon being absorbed or a photon.
Well, then it becomes inelastic.
That's true. Yeah. Or the photon. Photon with photon, it will not change the parity, right? So you cannot couple these two branches this way. Yeah.
It's maybe a simple question, but why does that scattering cause the degeneracy in the particles?
Well, so I mean, just think about your basic quantum mechanics. You have kind of two states, the blue and the red, and then put a matrix element between them. Then calculate blue wave function, red wave function, and coupling. And the energies of the two eigenstates will shift, right? So they were at 0, and they became not at 0, right? So this is sort of the anti-crossing problem, which you'll see a lot in qubits and whatnot. Right. So. Okay, so now another thing I want to tell you, well, first thing, of course, square root of 1 minus this, if you remember your trigonometry, this will become, the leading term here is sine phi. Cosine. So phi over 2 kind of goes away. But if there is no scattering here, if there's 0 scattering here, it will remain phi over 2, right? So theoretically, in extremely pure junctions, this can be achieved. Or, this is another way to understand Majorana, there is kind of an extra pi shift upon scattering with Majorana, which makes this matrix element strictly 0 when the junction is, infinite Majorana on the left and on the right. So that's how you get cosine phi over 2 energy in Majorana case. Matrix element sort of turns to 0 by requirements of topology of the band, of the scattering. Okay, so another thing about this function, of course, it is not sine phi or cosine phi purely, right? If you do a Taylor expansion of this function, it will have other components. Cosine 2 phi, 3 phi. So this is where the higher order terms come in. But the leading term, the strongest term, is always the first order term. And so if you plot it as a function of different tau, which here is called something else, actually it's, uniform contact with single mode transmission probability. Yeah, I think this is the same thing. So when transmission probability is 1, very pure junction, you see how it goes to pi like this, and then it actually resets and can go to the other branch. And then it becomes more and more sinusoidal, but it's skewed. It's a skewed function. So that means if you do a Fourier expansion of this function, you'll have other harmonics in it. But the leading term will be sine phi. And this is what I was saying about Majorana. I'm not going to repeat myself, but this one is 4 pi because you go through these points without scattering. Okay, so this is, yes?
In the other slide, the Andreev bound state does not depend on the thickness of the normal metal. Does it?
It does, it does. It depends on all kinds of things, right? This is just a cartoon.
But on real life, how long? Okay, if I wanted to connect two qubits with Andreev bound state, how fast they could be?
That's a good question. So it really depends on the material. So in our very good nanowires, we separated the two superconductors by 1 micron, even 2 microns, I think, once, and we still saw current flow without voltage. It was actually a surprise to me. I wanted to put the other one so far that it will not happen, and it was still happening. And then in some others, if it's a tunnel barrier, like in a transmon qubit, this would be 1 or 2 nanometers. And if you go to 3 nanometers, it's completely died off. So the range can be orders of magnitude. I don't know what's the longest people ever tried, but say from microns to nanometers. Okay, so this is sort of just to connect the two pictures with the cosine and sine in your head. So if I talk about current phase relation, it's a sine, a conventional one. But if I do what is called Josephson energy, I have to do this integral of the work done by raising the current. So if you ramp the current, there is voltage. That's described by, I didn't introduce it, but there is a second Josephson relation which says if you change current, there is voltage. So I have to do this work. By the way, this slide is from Yuli Nazarov. I forgot to acknowledge him, but he allowed me at some point in the past to use this slide. So I'm grateful to Yuli. Yeah, so you have to do IV dt, integral of work, and actually VDT is d phi. We will talk about it later in the course. Just for now, just believe me. It's called second Josephson relation. And if you do this integral, you can see that I as d phi makes it from sine function into cosine. That's all I want to say. So the minimum energy will be at 0 phase difference right here. So that's a conventional Josephson effect for you. Questions? Okay. Okay, so let's talk about the first example, unconventional. Anybody know pi junctions? Yes, Professor Ostrovsky knows pi junctions, I know that. Okay, so this is what I did for my PhD guys. Okay, so it's not the newest effect, but it's an absolutely beautiful effect. Okay, so I'm really happy that you are not so aware of it. That I can start talking about it again, because for a while I was like, oh, okay, pi junction. It's kind of like Majorana now. It's like, okay, another Majorana talk. Come on. I don't want to hear about the guy who jumped off the boat and particle, antiparticle for the nth time in the last month. Okay, so there you go. So here, a conventional junction, energy difference is at 0, is minimized. And so that kind of makes sense, right? No phase difference between the two barriers and no current flowing, and the energy is the lowest energy state. Makes sense. However, in the pi junction, we flip this sign here, we flip this sign here, and suddenly the minimum energy is not at 0, it's at pi. Well, of course, at pi we also have no current, just like at 0, but it's kind of weird, right? The junction energetically prefers to have the wave function do a flip from positive to negative, like that. And it has implications when you put the junction in a loop, right? It's like a pi shift. The integral around the loop should be 2 pi, but you insert a pi shift, so things happen. I'm going to talk about it in detail in the coming slides. Okay? Yeah, so this was what I just said. Conventional junction, very reasonable. So we talk about the condensate here, coupled like this. This is the lowest energy state. Now imagine there is something that prefers this lower picture over the upper picture. That's very strange. So I was very excited to work on it, and I still am. I'm still chasing some pi junction ideas 25 years later. And so, interestingly, people identified quite a few mechanisms how this could happen. And this is an incomplete list of them. But if you've seen these pictures in your literature studies or maybe in your research, I just wanted to flash them, and I just don't want to go through them all other than to say that there is more than one way to make this happen. And some of them go, the theories of this are sometimes pretty old. An experiment follows in like 20 years or so, sometimes faster. And this famous example, there is a pi shift in this loop, but it's not a pi junction. There's two junctions, neither one is a pi junction, but there is a pi shift when you go around the loop, if you know about this experiment by chance. So I'm going to talk about the second one, because that's my PhD thesis topic, and it works like this. For this, of course, we need something special to make this happen. Something special is a magnetic barrier. So now we have a superconductor, next to it a ferromagnet, and in a ferromagnet we have exchange interaction. So in a ferromagnet, bands are split like this. The spin-up band and the spin-down band are split vertically by exchange coupling, by many-body effect. Now, superconductivity, yes?
So ferromagnet electrons also can propagate.
Yeah, it's a ferromagnetic metal. Yes, thank you. Yeah, although this would also work in a ferromagnetic insulator, but in this case, let's think about the metal. So in this metal, there is a Fermi level where electrons live, and of course, Fermi level balances itself out at some value, well, electrons that make the Cooper pair would live at near this level, and so for spin down and spin up, they will have different momentum. So in a standard metal, the Cooper pair for spin up and spin down will have the same momentum. Actually, Cooper pairs are coupled plus k and minus k, so it will be a red dot on the left and a red dot on the right. It's plus k and minus k, but it's not exactly plus k and minus k because there's this delta p between the two branches. And we know what is a wave function of a particle with momentum. Right? I told you wave function can be described by one number, amplitude and phase, right? One complex number. Here, amplitude and the phase is like a propagating wave, right? With momentum, IQX over h. And so one has this momentum term from the positive branch. The other one has momentum term from the negative branch. It's this one. Well, I think it's the other way around. This one is this one, and this one is this one. And the amplitudes are exactly the same. So what happens when you add these two things together? Anybody recognize this function? Cosine. Right. A real. So all these I business complex numbers winding of the phase drops out. It's a real oscillating function, oscillating in real space, away from the barrier. Here, it's constant. Enter the ferromagnet, begin to oscillate. And of course, in real system with scattering and so on, it also decays. It decays away from the away from the superconductor due to scattering, due to loss of coherence. I mean, another way to think about the proximity effect, which is induced superconducting properties in a non-superconducting material, is that Cooper pairs is a phase-coherent object. Spins are up and down, and momentum are locked, and they're the same phase, right? They're part of that wave function condensate. You fly out as a Cooper pair, and you begin to forget that you're part of the same Cooper pair. Electrons evolve separately. And after a coherence time, or a coherence length, they completely forgot each other. Their phases are off by pi, or 2 pi, or something like that. And they're no longer a Cooper pair. But if you put another superconductor here, and they still remember each other a little bit, you can recapture them and recondense them as a Cooper pair. So hence there is this cosine term. Now, this is not the cosine phi, right? This is cosine x. It's an oscillating wave function and some decay. And it's interesting as this decay, this is a calculation done by probably Boosdin for the first time for a diffusive system, right? I told you in nanowires we have very clean crystals, electrons propagated for hundreds of nanometers without scattering. Back in the early 80s, that was not possible, almost. So people always did, all the theorists did an extra step, extra work, average out all the scattering possibilities and produce a beautiful formula for a diffusive case. And so there is a diffusion constant here. So electrons come out of the superconductor and they start doing, and there's also exchange coupling here. And there is temperature here. So this temperature was a beautiful effect because I could control whether it's a 0 or pi junction with temperature. And I did not discover it, but it was a beautiful thing to play with this. Temperature became a control valve. Okay, so now, okay, another poll. Can you give me hands if you're a theoretician? Very good. Experimentalist. Okay. Okay. So this is for, I guess, both of you. So this is how you have to make these things, right? You have to make them, to measure them, you have to make them. And so my students in my lab, you know, averaged over PhD is 50% making these structures and 50% measuring them or writing papers, etc. And it's not even, right? So first you can spend 2 years trying to make something that works. That was certainly my case in my PhD. Nothing was working. And then you measure, sort of for, once it starts to work, you measure. So we have to make a superconductor, ferromagnet, and to make a Josephson junction, another superconductor, SFS junction. And the goal is to put the ferromagnet of the right thickness to right here, so that the wave function bends to pi, positive to negative, that's pi, right? So this thickness, or maybe this. So precisely control the thickness. And so this is a multi-layer nanofabrication process. I will show you more of these kind of samples as we go along, but basically you start with something that is just a wafer, a holder of your device. In this case, it played no role other than just to be a table, a substrate for the junction. And then put a layer of superconducting niobium. Niobium is just a metal that's become superconducting, about 10 Kelvin, 9 Kelvin. Then you have to put ferromagnet, which in this case is copper nickel. It's nickel diluted with copper. Pure nickel is too strong to be too thin. And you can see this niobium is everywhere. This copper is patterned. So there is a process for patterning called lithography. Right. And the others are like, whatever. I don't care. I don't care how you make it. What's the Hamiltonian? Okay, yeah, so this is like, you know, this is like, oh my God, months and years to make these patterns. And then there is a window, dielectric window, and then inside you put another niobium, and then you kind of you have to explode it through the window in a pretty violent ultrasonic process. So you make this SFS junction. And this is another way, oh no, this is the exploding here on this side, sorry. Here we start with 3 layers that go everywhere, 1, 2, 3. But then we have to define the junction because we need to make a top contact and a bottom contact. We need to make the contact to the bottom layer to put current through it and then go to the top, right? So we make to the same goal. So we edge down the tri-layer here, then backfill with silicon oxide, and then put then we explode, and then we put niobium on top. So I did this, and it kind of worked, and our friends in Chernogolovka did this, and this worked even much better, and they were the first ones to discover this effect. Valery Razanov and his team, Volodya Boznov, etc. And so I struggled with this, and I made like, I don't know, hundreds of these, and they probably were pi junctions, but it was like difficult to see because there was no temperature effect. And then Boznov sent me a few of these, according to my designs, and my entire PhD is pretty much written on these samples. Yes?
Yeah, how do you insert the bottom electrodes, like for the low state?
Right, so somewhere far away, you can just put the contact directly to it.
How did they do silicon oxide window?
Here? So they made another pattern. I actually sent them all the patterns, how I wanted them. And so in this pattern, there is a polymer that blocks off this area, and this area, and this area, and then silicon oxide goes down only where it should be.
It's like a flake of silicon oxide?
Oh no, it's deposited in a vacuum chamber. It's sputtered, if you know what that is. Yeah, so now it's popular to put flakes of boron nitride as a dielectric, but we didn't have that, right? So we made, so you put substrate actually upside down usually, and below it you make either, so the easiest one to explain the electron beam evaporation, right? So you have a bolt, and then you shoot electrons at it, and you heat up with high energy, you heat up the boat, melt the metal in it, and it starts to evaporate. And because it's in vacuum, it doesn't evaporate like steam from your cappuccino, but they go in straight lines, and they make very smooth films. And this is how this thin film processing is done. Right? So we have 5 or even more different machines for making thin films with different ways like that.
It's always optical lithography, yes.
Well, yes, in my PhD, optical lithography. Now we do electron beam lithography and other things. Yeah, so this is, I guess, also good to see. These are micron-sized junctions. So no talk about single Andreev modes. That would be something like 10 or 20 or 50 nanometers, right? So we are orders of magnitude. So now, 20 years later, we work with those, with tiny ones. In my PhD, it was microns. So it's huge. Now my entire, I don't know, I can put probably 100 junctions in this area. Okay, and this is a beautiful effect. I think a bit fine-tuned data, but still, mostly this is exactly what happens. So you see the oscillation, right? And this is as a function of thickness. So Boznov, he made these tri-layer junctions of different thicknesses, and he was mapping out the critical current, the maximum current. Hopefully he did it at the same temperature, but I think not quite. He kind of went to the maximum. So you see it, first of all, that it decays. And this is a logarithmic plot. So it's a pretty fast decay of the signal. And that's the overall decay. As you put the two superconductors farther apart, the thing decays. Now, in addition to decay, there is special points where it goes to zero, essentially, because this is, again, logarithmic plot. And so the idea is that this is 0, this is pi, this is 0. So 2 1.5 periods of oscillation they were able to map out. And you can see somebody asked what is the thickness. This is the 30 nanometer thickness. It's a disordered alloy, so it's a lot of scattering. Maybe every second atom you scatter. It's a very disordered, very diffusive regime. And so you have to use these Usadel equations, which I'm not going to talk about, but you can look it up.
You say this is a very large junction, like 50 microns.
That's the area, right? And this tunneling direction is 30 nanometers.
So
Right?
how well can you maintain the thickness of this area?
Good question. So I have some slides about that. So it's not perfectly smooth, but apparently it's quite smooth. Yeah. So my fit to some model gave sort of an 1 angstrom variations. But this wasn't the samples. So some magic samples. Okay, so now what am I doing? It's a bit out of order, the slides. Okay, let's go here. So let's go back to this idea that how do we prove that it's a pi junction? So this oscillation is quite impressive, that the current decays and it has these nodes. You could already say, what else could it be? But it would be nice to see the pi shift with your own eyes, right? So that's what my PhD was dedicated to, seeing the pi shift. And so for this, one of the ways to see it is to use this fluxoid quantization. And I already mentioned it, that the wave function of the condensate is single valued, like any wave function in quantum mechanics. That's a legitimate wave function. And so if you go around the loop, you have to go to the same point, and that means if you have a phase winding around the loop, that has to be 2 pi. Now, that's a simple way of saying it. In the presence of current, we have to talk about fluxoid, not flux. Okay, this slide is from Ustinov, Alexei Ustinov, and he calls it flux, as he is another experimentalist, also from Zaporizhia. Kind of just like me, but a little older and also a lot more distinguished. But anyways, if you integrate, let's say, vector potential around this loop, that's flux, and flux has to be quantized. Let's keep it like that. Now, if you put a pi junction here, you have half a flux quantum. And you need to generate another half. And the only way to do it is to get the condensate moving. So there is spontaneous current. Okay. Ah, yes, this is my slide. So here is fluxoid. Right? So there's okay, so in a loop, you have a phase, I don't know, it's still flux. Okay, anyways. There is a phase winding around the loop plus a jump across the junction. Okay? So that's the equation, okay? And this has to be 2 pi. 0, 4 pi, minus 2 pi, something like that. And we already have a pi here. So that's the problem. This is the energy view, right? So you can do the same with energy. Again, very easy to think about it. Remember, Josephson junction gives you a cosine. So cosine will be minimum at 0, and this kind of wiggle, and the overall parabola, that's the inductance of the loop. So you have the inductor plus the Josephson junction. Josephson junction has Josephson inductance, which is this cosine function. Phase difference is also connected to current flowing around the loop. So either current or phase difference. So if you add this circulating current and the phase difference, you get not just a parabola, that's just a pure inductor, but these kind of wiggles. And this is also written here. Josephson term and just the inductive term. But now instead of current, we substitute this in terms of flux from the fluxoid quantization. Now, the idea is that if we put a bunch of pi junctions, there will be currents flowing in loops. And we will be able to see them. So we use this tool. In my PhD lab, they discovered this sort of scanning squid microscope. I will talk about the squids later, but for now, just think about it as a pickup loop, which is micron size. Here it is. And a squid, which is a very sensitive Josephson junction-based detector of flux. So if you scan squid over the surface, you can see all these beautiful patterns like superconducting vortices and various screening currents in superconductors that are generated by either flux, quanta in the film, when the fields come out and generate flux in the pickup loop, or by screening currents flowing around superconductors, because there's also Meissner effect that I didn't mention, but that's an important effect for superconductivity. So if you put something superconducting down, turn on a bit of field, you can see various currents or vortices, and you can image them with a scanning squid microscope. So in my PhD, what we did, I designed this pattern and then sent it to designs to Chernogolovka, and they printed this kind of structure, which is a fully frustrated array of cells, 6 by 6. Each cell has a phase shift of pi, because each cell has 3 junctions. So the green is a ferromagnet. So this cell has 3, this cell has, oh no, this picture is not fully frustrated. This cell has 2, this cell has 3. But I think this picture, the little yellow squares in the bottom picture are ferromagnets. So I think in this array, each cell has 3. So each cell will generate 3 pi or minus pi or frustration. And so it means each cell you will have a circulating current. And so here now is a function of temperature. In zero junction state at high temperature, remember I told you it's tunable by temperature. So at high temperature is no pi junctions. I can see the array itself very faintly, and that's the screening current from the Meissner effect in the superconductors. And then I cool it down below, and it lights up with this checkerboard pattern. Almost perfect. Here is a defect. So one current circulates this way, the next one circulates the other way, and then again, and then again. So this is kind of a demonstration that pi junctions generate flux due to pi shifts. That's, to me, was absolutely beautiful. Here's some more pictures, all kinds of things we wrote, we fabricated, and for instance, if you say, oh yeah, well you have a vortex in each cell. Maybe it's not from pi junction, maybe there's just some background field that generated this. Yeah?
Can I ask like what do you mean by the frustration patterns?
Yeah, so frustration patterns are like this. So each red cell would be with an odd number of pi shifts. And each white cell would be with an even number of pi shifts. And so the hypothesis is where we have an odd number of pi shifts, we would have to generate some current. And when we have an even number of pi shifts, there is no need to generate current. It's energetically favorable to have no current. And so then you know what you designed, then you look in the scanning squid, and I guess colors don't represent very well, but you can see here, like you expect 2, and you can see these lines. Here you expect 1 in the corner, and you have these lines. And here you expect all of them. And here it's two lines like this. So really, whenever we put the frustrated cell, we have a vortex, and where we don't, we don't. So it's a smoking gun proof. Smoking gun? Like when, this expression smoking gun? Some people? Everybody. Like you walk in, there's a body, and there's a guy with a gun, and the gun is smoking. It's like, I didn't do it, what about this? Anyways, I'm talking about it because if you go to archive, you can see a paper where I show that smoking gun evidence can also be fine-tuned to look like that. But in this case, it's my work, so it's correct. Right. Yeah, so there's some more data here. Here, really, you can see as a function of temperature. This is a pi transition as a function of temperature, 0 state to pi state. And as we cool it down, this happens. The pattern is not there at high temperature, and then at low temperature it appears.
What is the red light?
It's guide to the eye. Oh, no, I think, no, so, I don't remember.
It says root means square magnetic flux, so apparently it's a simple
Yeah, I mean-
calculation for the expected critical current.
So the flux doesn't appear immediately. That's, you see how it doesn't go from nothing to pi. It goes according to some curve, and that's because it's an energy competition. Let's see if I have a slide on this or not. No, I skipped it. Yeah, no, I remember what this is. So imagine you have a pi junction that wants to be in the pi phase, but the inductance of the loop is so high that to flow so much current to make the whole thing go into pi phase is just energetically makes no sense. It's easier to flip the pi junction into its disadvantageous zero state, because that costs less energy than running the current in the loop. Right? And so you can calculate this, given the strength of Josephson effect, you can calculate at what point it becomes advantageous to start flipping the pi. And when that energy saving is more than the energy lost by flowing the current. Right? And so you can do this calculation, and yeah, it's all my thesis.
What is this graph on the top left?
IC versus temperature, right? So this is a,
Critical current?
yes. So this is,
Why the
because it goes to pi. So now I can plot it as negative because I know in this phase there is a flux appearing, which means the Josephson current is actually negative. Right? So this is just go back here. So one way to say it is that energy minimum is at pi, which is this expression. Another way to say it is that just the current critical current is negative. So you just take the pi out of sine phi plus pi and put it in the amplitude of the critical current.
Okay.
Yeah. So, for instance, in this measurement, what they were doing is just sending current through the junction and measuring the amplitude. So they could not tell which way it goes, where it flips. Right? But we could. Okay. So this is very nice. And yeah, so if you, another measurement we did, here actually pi state was the high temperature phase and zero state was the low temperature phase. And we put one junction in loop and measured directly the current phase relationship, right? You pass the current and you measure flux through some inductive coupling with this squid. So this is how the sample loop, this is the loop. Pass the current here, there's a ferromagnet here. This is a tri-layer junction view from the top, 100 micron scale. This goes to flux detector through this inductor. It generates current in this loop and it's picked up by a flux detector. And you get these kind of curves. Here it's when the Josephson effect is too strong, it becomes hysteretic, multi-valued, but at lower, it's just basically you have an inductive response, linear response, you put current here and it couples linearly to this flux. And on top of that, a modulation due to Josephson effect, which is a wiggle. And then you do these wiggles from high temperature to low temperature, and you see these wiggles here at high temperature, they are going like this, then you go through, it disappears, goes to nothing, and then when it reappears, it's shifted. Here was near the cusp, and here is flat. And you can subtract the linear slope, and you see that you go from pi to zero, from 0 to pi. And then another thing you can look at, okay, so there is a point at 359, at 3 Kelvin. By the way, this is another thing, right? Now in my lab we do millikelvins. Back in my PhD we did big junctions, high temperatures, kelvins. Yeah, we licked lead with our tongues and did all kinds of crazy things. Right. So when the first order effect disappears, then you can ask, what's behind it? Is there a second order effect? Right. So that was sort of the reach question of my PhD. If we kill the first order, can we see second order Josephson effect, which would be like this, sine 2 phi. And so you can fit these curves, and in this experiment, the IC2, the second amplitude, came out to be nothing. No second order Josephson effect. A little disappointing. But there is a continuation to this story. Okay, so now, how much time do we have?
15 minutes.
Okay. So maybe no break then. Okay, so now I set this aside for a few years. I did semiconductors, quantum dots, spin-orbit interaction. I learned in a postdoc that I'm not going to talk about here. And then I got an opportunity to think about Josephson junctions again when I moved to Delft in the Netherlands as a postdoc. And I was thinking about this pi junction, the exact same idea, except the bands are split not by exchange coupling in a ferromagnet, but by external magnetic field. You can do the same thing, right? You apply magnetic field, and it will Zeeman split the bands, and we can have the same effect. And now the control knob is not temperature, it's magnetic field. The bands just gradually split, and at a certain field, which we call B pi, we go from 0 state into pi state. That's the idea. Zeeman pi junction, the driven, same physics, right? The oscillating wave function, real oscillation, driven by field. Except there is a problem with this idea, and it's that superconductors and Cooper pairs and wave functions really dislike magnetic fields, dislike it. And in many ways, right? So first of all, this effect already is bad for superconductivity, splitting bands, and you have to be at the same momentum, so same energy, so momentum starts to drift away. That's bad. On top of that, there's orbital depairing, which is because you put flux through the superconductor, and it dephases Cooper pairs, because as they fly around the two electrons of the Cooper pair, they pick up different phase because there's flux going through. So that's called orbital depairing, due to motion of electrons in the material. And so there was this very nice paper, which is about something else. Back in 20 years ago, there was no culture of writing a paper like, this is not possible. So they stuck it in section 5 of the paper. This beautiful measurement of orbital depairing in SNS junctions, not ferromagnetic now, just conventional metal like silver. Aluminum, silver, aluminum, SNS junctions. And they measured critical current decay as a function of magnetic field. Now, the thickness of this aluminum was, I think, 20 nanometers. So 20 nanometers of aluminum, you put film this way, flux this way, parallel. And already you can see by about 100 millitesla, certainly 200, it's gone. It's all depaired. And if you calculate what field it takes to put a flux quantum in this way, it's sort of close to that. So it means we have a limited range of field to work with before it decays and disappears. And there are also these calculations, again, for diffusive regime with a D, back in the 2000s, everything diffusive, now everything ballistic. So different, simpler formulas. Like in the ballistic case, it's just VF over L, the speed of electron divided by length. Right? In diffusive case, it's square root D divided by chi, tau T squared or something. And there was a 16 also here that they calculated in this paper. So to reach d pi, you need to have 16 times the tauless energy A Thales energy is the time it takes electron to cross from one superconductor to the other. Okay?
This is like exact number. Exact.
It's just from this paper, but this is what I had. Like in 2008, I was like, oh, can we make this experiment? So let's throw some numbers around, right?
It's, each bar is the top of the
Yes. Thank you.
Just
Yeah,
the-
yeah, this is from some group meeting slides, yeah. No, it's like real stuff, right? Like historical records. So, and you can see here, thickness, right? So to put a flux quantum in, length of the junction times thickness. So length, Cooper pairs go this way towards you, length times thickness. And you have to put a flux quantum in that to depair, orbital depairing. That's the heuristic. And then I write T is 0 for graphene or carbon nanotube, right? That was pretty naive, by the way. But at the time, right? I was like, okay, so we now have 0. This is 2008, right? Graphene was discovered in 5, 4, yeah, something like this. Right? So this new material, I remember. Was it Game I think came to Delft, and at the time graphene was just like a new thing, interesting, but not everywhere like now. And I told him, I have an idea where we can use graphene's thin thickness for something useful, for pi junction. And he said, there are many things you can be used. Oh, sorry, I have to. There's an alarm at my house in America that went off. I think I have to call them. Otherwise, police comes. Okay. Okay, so take a little break. It's not working. Okay, well, you'll have to deal with it. Okay, so right. So I did the numbers. Yes.
Do we really need to that phasing should be 0, or it could be like just a small?
Well, I want to win over dephasing, right? I want dephasing to be here and pi junction here. So I wanted to dephase slower and have the steep B pi at lower field, like here, for instance. Decay like this and pi transition at lower field.
Yes, but
That's
for
the
that we don't need like to T equal like exactly 0.
No, no.
So it could be just really small, like some 2D material.
Yeah.
So
Could be.
okay.
Absolutely. That's the idea, right? So here, okay, there's some numbers. So on the one hand, the bad thing about graphene is G factor is 2, like the free electrons. So you have to go to pretty high fields. It's a pretty clean material. So mean free path is long, and that means Thales energy is large, typically. So you have to make it a very wide junction, so 2 superconductors far apart. And these kind of heuristics that I was using, right? And I was using very thin thickness. I wrote no orbital depairing. I now no longer believe that, right? So it's not correct, but I wrote no orbital depairing. But I need to go to 1 or 2 Tesla. I need superconductor to survive to high fields. So that's kind of the game. Carbon nanotubes, similar considerations. High Fermi velocity, long mean free path. That means large Thales energy. But there's sometimes large G factor and spin orbit, which turned out to be a useless type. But we could try a long junction, like 2 microns long, in a very clean nanotube, and maybe we can reach, and we tried that. It was inconclusive. And now nanowires, the same things we use for Majorana, right? Nanowires from Majorana. This one is indium arsenide, so the G factor is actually higher. So you need to go to lower field to achieve Zeeman energy that is the same as for graphene. But they are thicker. They're about 100 nanometers, 50 to 100 nanometers diameter, right? So graphene is thinner. These ones are thicker. So if you calculate orbital depairing with this, kind of, again, puts you in a Tesla scale. And then, what we used for Majoranas actually was indium antimonide. So from indium arsenide, indium antimonide, the relevant thing here is G factor 40, even 50, even 60. So you can go to pretty low field, get a lot of Zeeman energy, and the geometry is the same, so it will dephase in 100 or 200 millitesla, but you have this chance, you have the hope to reach by junction state, by field, in this very clean nanowire, instead of by temperature or exchange interaction, etc. Right? So this is a non-magnetic material, non-magnetic. Okay, so when do I, maybe I stop here or?
5 minutes.
5 minutes, okay, yeah. So I will introduce these junctions to you and then we will look at the data tomorrow, okay? So these are really quite amazing junctions. These are not the ones we use for the first measurements, but these are the ones we use kind of right now in the lab. These are the nanowires, indium antimonide, and they are grown. We etch these trenches, which are notches like this, and we put particles, gold catalyst particles from which wires nucleate at very precise locations along the trench, so that the wires grow. There's a relationship between the crystal and the wire and the substrate, and because it's at an angle, they grow like this crisscross, right? So imagine we went from sort of laying down carpets of film, which is micron size long, to precisely positioning nanoscale particles of gold and nucleating these perfect crystals. And what's more, they're offset, right? So the front one is 100 nanometers closer than the back one. So they are like this. They're not touching. And the reason for this is the front one is shadowing the back one. And then superconductor, tin in this case, comes this way. And then the front wire is fully coated. The back wire, there is a shadow. This shadow is created by the front wire. Shadow here, right? So we make a junction, tin, indium antimonide, tin. That's the Josephson junction, like this. This is about 120 nanometers, which is the diameter of the wire. Why all this? Why all this crazy effort? So that we could have as pristine as possible interface here, without any scattering, and without processing, without putting in acids and solvents and other things that damage the crystal. This interface is very, very transparent. This wire is ballistic. Electrons travel from here to here without scattering, other than specular reflections perhaps. And there are no crystalline defects here. The surface can have some roughness. And you know, when we get into the Majorana business with these, they're so beautiful and so elaborate, but they're still not good enough for Majorana. But for this stuff, it's pretty good. Right? So it's also capped with aluminum oxide to prevent this tin from. This is another idea where there is a flake that shadows the wire. Okay, so this is the junction, kind of, and this is how we then make the full device. That's the substrate from before. Remember, there's a substrate like a table. Now, on this substrate, there are these gold electrodes that are very thin. These are 6 nanometers thick gold, and they're electrostatic gates. They can be individually controlled, put voltages on them. And then there's a layer of dielectric, in this case, hafnium oxide. So this is just the preparation.
Why do you use hafnium oxide?
It's a very high quality dielectric with a dielectric constant could be 20 or so. So it transfers electric field through very efficiently. And it's a very low defect, high breakdown voltage dielectric. It's a very convenient dielectric. Right, so we prepare this kind of elaborate substrate, right? Not just a plain wafer, but with all this stuff.
And you're depositing using ALD or?
Yes, hafnium oxide with ALD.
Thermal or plasma?
This case thermal, but yes, with plasma could be even better. Okay, so then this nanowire goes on top of this substrate. So this is the junction then. Underneath some gate, and there are more gates. This is tin, indium antimonide. And then you still have to make a big circuit, right? Eventually there is a current source which is a box like this, right? And this is a nanowire which is 100 nanometers. So there are these contacts, and they become bigger and bigger and bigger. Then there is a wire bond, etc., and to connect the circuit to do these measurements. So now I brought you from sort of early 2000s, where we made samples one way, into the more modern era. These results are, some of them are 5 or 6 years old, some of them are last year, that I will be showing you, and I guess I'll be showing you these results tomorrow. Right. Stop here. Let's see. Yeah, the next slide is. Oh, okay. Let's one more. So this is the data, right? This is not quite made the same way that I showed you, but roughly those steps. So look, magnetic field now. First of all, we have current surviving to about half a Tesla. Pretty good. So this is field oriented along the wire, like this. And it goes to 0, reappears again. So the idea is this will be the 0 state, this will be the pi state, maybe another 0 state. What is also interesting is that if I change the voltage on the gate underneath, I can shift this pattern quite dramatically, right? So look, here it decays and goes to something like this. Doesn't actually go all the way to 0, which is interesting. Maybe there's high order terms like sine 2 phi. This is between 0.2 and 0.3. Here I adjust the gate, goes down between 0.1 and 0.2. So what does that mean? Maybe I'm controlling the thallus energy, the energy that goes in the equation, right? The pi field is related to thallus energy. Maybe that's what I'm doing here. So this is data from the summer of 2011. And then around Christmas time that year, we got the Majorana data, and this was shoved to the side, and we came back to it like 5 years later to really analyze this data. When Majorana was coming, this pi junction stuff was like, who cares? Right? But now maybe this is the only real thing. But we'll find out tomorrow. Okay. Thank you.
Questions? Orbital depairing.
Yeah, orbital depairing. So you have 2 electrons in a Cooper pair, and they are locked in momentum and spin, and also in phase. Now they enter the non-superconducting material, and the phases and the spins in principle also, momenta starts to scatter, and the phases start to drift. Right? So after a time called coherence time passes, they forget each other. The phases differences more than 2 pi. Now, under the influence of orbital, it means inside the trajectory that they make, there is flux. And so there's vector potential current, which is related to phase difference. And so as you travel through field, this dephasing happens, let's say, faster. Because you accumulate not just dephasing due to thermal effects and things like that, but also just to vector potential.
One more thing, you wrote a formula for it that depends on the length of the sample, right? But should depend on the trajectory of electrons, right?
That's right. So the formula I wrote is very hand-waving, right? So if I assume that the electrons really explore the entire junction, like it's very clean and they can really bounce everywhere. And then there is the geometry of the junction, the cross-section of the junction, versus when I put a flux quantum through that junction, that's when the 2 pi happens, right? But in a real, I will show you tomorrow, in a realistic geometry, we have to kind of average all the trajectories to calculate more precisely the depairing.
Okay, thank you.
Pavel?
You said that, for example, for graphene it's too clean and the diffusion constant is too large. Okay, so can you make it deliberately smaller by adding some disorder to the system?
Yeah, so in the end, we tried with graphene a bit, and our junctions were pretty disordered. And it's published in some PhD thesis. Disorder makes it also harder to see the pi junctions because the patterns become kind of disordered when you apply field. Right? At zero field is Fraunhofer-like, but then in field and with disorder, it becomes a mess.
Anton?
I'm looking at this sort of picture and I'm a bit confused by the fact that it's not symmetric with respect to current
Oh, yes.
zero part.
Yeah, I did not talk about this. So this is obtained by sweeping one way only, like this. And so in Josephson junctions, depending on the junction resistance and
So
capacitance,
it's hysteresis.
yeah, there is a hysteresis. So the switching current to finite voltage state and the retrapping current are different. That's the RSJ model
Yeah.
that I did not cover. I apologize. If you want, I can talk about it. I certainly have some slides.
You had a recipe for the Marana fermions. Like, could you tell a little bit more in detail how it realized in the experiment? It's usually like quantum dots and superconductor quantum dot, and why people in the experiment cannot see the Marana states? Because in theory, it exists, but in experiment, nobody showed like that they really exist.
Well, some people disagree, but I agree with you. Yeah, so for Marana, it's not two superconductors like we talked about today. It's one superconductor, and the interesting things happen on the edge, here and here, on the two sides of the superconductor. And what you have here is a bound state, a Andreev bound state, we talked about, but it's bound to zero energy too. It's not at any energy, it's exactly at zero. And to see if it's there, you can tunnel into the end. And if there is a state at zero, the tunneling current will be a little bit higher. And so that's called the zero bias conductance peak. So at zero source drain voltage, at zero energy, there is a bit extra current flowing. But there is other ways to get the zero bias peak. And some of them don't apply to this situation. But there is one that's really potent, is if at the end here there is an unintended bound state that happens to be at zero. It's not a Majorana, it just looks like Majorana, but it's not of this topological origin. And that's what people are looking for, because we don't know where Majorana is a priori. We just look for a zero bias peak. And when we find it, we say, well, this is Majorana. Right? So it's like looking under the street light for the keys that you lost.
And how people in experiment could prove that they state are topologically protected, or to see if
Protected is
they're
hard, right? You need to do some kind of grading. This is hard. But to see that it's related to some topology of some bands, one simple way, which is also not free from problems, but because Majorana here are part of the same wave function. So if you tunnel on one end and simultaneously tunnel here, there should be some connection between the two measurements.
Thank you.
Yeah, next summer school I talk about Majorana. The rest of it. You can have, there's like 25 different YouTube things that I recorded about it. If you really want to hear the story in the same voice.
Okay. Thank you. And now we will have a welcome tea party at the Josephson Institute. And I would ask participants who are local from Ljubljana, I don't know
the place to help all other participants to reach this point.